will ask questions. So you don't ask. And so here I was with this arch model, and I wanted to go on with passing some data on it and do some estimation, look and see what happens with essentially these coefficients and so on. So that's what we want to do. Alright. Then here we have the y, which is, what did I define that? That's y. Okay, so that's the dependent variable. So the mean I will leave as a constant. I didn't mind that. So sort of we have a constant mean. And but it could be AR, could be 0, could be whatever. Alright. Let's go to the number of lags. So let's lag for the mean. So let's go for the P and Q. Alright. So O is an asymmetric term, which is by default is 0, and then I haven't told you asymmetric Gaussian. So that's sort of off for the moment. But as I told you, so P and Q are other way around. So P is for the MA part, right, which is in the MA, and Q is for the AR. Alright, so sort of that is a little bit different. So that's other way around. So here I reset P equals 1 and Q equals 0. So that will be an arch 1. So that's sort of what we have. And then we also fix the volatility. By default it is Gauge, but I will just write it in so that we remember that we have a Gauge model. Alright, so that's sort of what we have. So the model is defined. Let's take this package off. So we import it. And let's do the model. So that's an arch 1 model. So we can directly do the fit. So let's say dot fit. And then on fit here, we can actually say, show us how we do the optimization or not, and so on and so forth. So here I leave the display on. Right? So I could have this off, and it wouldn't have shown me the optimization. But here, well, we just see. So there are 9 iterations, right? And then there's a Latin function, right? And then we go, right? So that's sort of what we do. So that's the current value of the objective function, 9 iterations. That's actually pretty fast, all right? Right. So I have 9 iterations and 9 steps. Sort of then we come to the ultimate value. Well, seems okay. So here it says optimization validated successfully. That's the exit code. So it really converged within the tolerance that we have for the optimization. So what we can do is to print the results.
Some of the laptop cannot run the from arch model.
Alright. But you imported it?
Yeah, it usually say that no one may have. I used to have.
So people use store. So it means you're going to have to use store. But you have it? Magic. Right, so you can use the pin install Arch, then you will be good to go. then here we have the model, and these are the estimations. So the dependent variable is the S&P 500 index. We have a constant mean. Volatility model is R, so distribution is normal. Method for estimation is maximum likelihood, ML. Then you have AIC, BIC for this model. And that's it. So good to go. Right? So here then we have the mean. That is this. Mean. Right? Which is like very big positive. 8%. Well, this is sort of long term and so on and so forth, right? So if you were buying this in 2014, keeping it till now, then you would have earned on average 8%. What's the average return? Whether you would have lost your money or not, I don't know. Also because at times you may have lost a lot. Or left with nothing. You can't continue. This is omega and alpha 1. Omega is alpha 0 in this notation, and alpha 1 is alpha 1. So here then we have alpha 1 to be 0.5. That's essentially significant. Right? That's a confidence band. So here it seems like that if this model is a good model, then the persistence measure is like 0.5. I don't believe it. Persistence measure for this type of processes, sort of data, this is a market index, is much higher. Because there are market indices that are more persistent in terms of volatility. So the volatility doesn't forget the past so easily. Right? So that remains for a longer period. So that's sort of why I don't accept that. But on the other hand, so if you remember sort of the autocorrelations, let's look at them. So they are like so. But this doesn't look like to be an AR1 model. Right? So if it was an AR1 model, then the first autocorrelation should have been 0.5. It is 0.5. That's this number, 0.5 that we just saw. The second should have been 0.5 to the power of 2. 0.25, but it is not. Right? And then the third should have been 0.5 to the power of 3. It's much bigger. It's like more than 30. Right? So it means that the model that we have potentially is not a good one. Maybe an arch 1 is not good. Maybe we should use arch 12 or arch 10, something like so. Right? So a bigger number of basically lines you would need to have here. Let's maybe look at an arch 5, just for the fun. Alright, so let's say I have here 5, and this is 5, and this is 5. So, boom. And we have the 2, and look, the coefficients are all significant. It's alpha 1 up to alpha 5. Right? So here, if I sum these coefficients, well, remember that the summation of the, if you have an AR2 model, just as a reminder, so this is the persistence measure for an AR1. And the persistence measure for AR2 is what? How do we calculate it? What is the persistence measure here? Sir? Persistence. Let me talk about that, okay? So let's say xt today, well, the value of this is 10 today. And then let's say this is 0.5. Just say 0.5 or 0.9. So let's say it's 0.9, and today is 10. Then this 10 will actually load itself into the future for everything of me when it goes smaller. Fully, right? If I'm not, if this coefficient is smaller, then look, half of it will go to the next year, say if it is 0.5. So, and you know when this is 1, then you have an integrated process of order 1, which is very persistent. Right? So the prices are very persistent. This is what you know. So that is something which we call the persistence measure. And well, if I look at, if you remember, so the autocorrelation functions are phi to the power of j. Right? When j is higher, then the autocorrelations are stronger, right? So they don't go off so easily, so the process doesn't easily forget its own past. If it is 0.9, then 2 days ago will happen to affect tomorrow linearly with correlation of 0.81, 0.9 to the power of 2. So that means that it's more persistent compared to the case where phi is 0.1, because 2 days ago will happen to affect tomorrow whether or not the correlation function of 0.01. So that's much smaller compared to the other. So this is something which we call it a persistence measure. The higher, the more persistent. The lower, there is no persistence. If it is 0, then there is no effect of yesterday. Right? Yeah, that is the persistence measure. How much today or how much past is moved on to the future. That's the persistence measure. And that's the same as this. They are, well, I mean, if I had here, if this was off, arch 1, then this would have become the persistence measure, which we estimated for S&P 500, and that was 0.5. Roughly. And now, I'm saying, okay, so what can we do with this? So how much past, well, how does actually this process remembers the past? Right? Let's distribute across 2 lines, the past, across yesterday and 2 days back. Right? So if I want to have a so-called persistence measure for an AR model of higher order, we are more parameters. Right? And what we generally do is that we sum them. Right? So the addition, the two together, becomes the persistence measure.
So, yeah, about that plus, because we have two different descriptions about that.
Yes.
One is the absolute value of each one plus,
Right.
and the other is the absolute of the plus
Yes.
inside. So, you want to ask about the difference?
You mean the stationarity conditions, or I was actually thinking of something else?
Yeah, I just remember something about that.
Sure.
Yeah, sometimes
Is
it's.
this related to the characteristic polynomial?
It is. I will now explain.
Đó, kinh điển.
I'm going to look at the book, but the older version. Because there is a picture. This doesn't. You have Hamilton, the book. Well, you know Hamilton, right?
We heard a lot from Jonathan from the semester course.
You heard it well, but this is, I mean, I couldn't find this. But then on the very first page, the cover of the book. Right. So if you take a look, maybe if I look, then I will find it. So there is a picture. And that picture answers your question. It's on the very first cover. And that is something like so. Say we have C1, 2, it looks like this.
you remember? I mean, if you have seen the book, then you should have seen that.
The condition.
This is the region. And if V1 and V2 are in here, that's a quadratic function and so on and so forth. Then the process will be weakly station. So one of these conditions, so if you look at this is one of these conditions is that, which is irrelevant, that is somewhere here, right? That is that the absolute value of V1 plus V2, if I remember correctly, minus 1 is smaller than every other. That's all right. So that is a smaller than 1. That's sort of the absolute value. Sorry, I don't remember it correctly. I have to do the derivations. I don't have it now. That actually has something to do with the absolute value of the difference minus 1. Right? Or maybe something like this. Smaller than 1.
Yeah.
I think it is that. That is one of the conditions. The absolute value of the summation should be smaller than. So indeed, if you rewrite this in Hamilton's notation as a sort of a bivariate equation, x is a function of the past, and then let's say xt minus 1 is equal to xt minus 1, that's another equation, and xt plus 2 minus 2 is equal to xt minus 2. So that would be a vector of 3. Then you will have the characteristic polynomial equations in a matrix format. So these are the notations of Hamilton. If you don't remember them, it will be hard to understand what I say. Should maybe do that. But let's just stay with this. It's something you remember. One of the conditions for stationarity is this. And that is indeed some component which shows up in transferring the future into the past into the future. Pretty much like phi1 when you have just one coefficient pass that does. Okay. So that becomes the cumulative, so to speak, effect of the past on the future, if you want. So that will be a little bit maybe easier to understand also. And that is something we should put in the persistence measure. Now, how much the past, it doesn't matter that the past is yesterday, it could be yesterday and the day before, happen to affect tomorrow, cumulative. Right? That's a dynamic effect. Okay? It's a dynamic effect of the past on the future. So, now let's take this. If it was ARP, then it would have been phi1 plus phi2 plus phi3 and so on and so forth. So we would have added over. And that's the same here. So if I want to look at the effect of the past shocks on the future values, or the effect of the past shocks on the current, indeed conditional variance, and the effect may be alpha 1 plus alpha 2. So how persistent indeed the process is. Right? So far so. So, this picture I didn't find, it's not a problem. And then here, so if I want to calculate the persistence measure, then I will add this. 22 plus 17, 39, 49, 40, 54, 74, plus, so that's 94. Roughly, 0.94. And so if I put these two coefficients together, additively, add them together, then I get the persistence measure. And this persistence measure is a little bit, well, sort of closer to how our market index would look like, because, well, they are all significant. Right? And then the summation, which is roughly 0.94, indicates that you have a persistence measure of this much. Right? So, but again, what? Maybe we add more. Maybe let's do an BIC, AIC to check whatever model we should actually use. All right, so let's do model selection using AIC, just to see how many DAX should we do. Okay? So let's
first I want to make sure that you understand the estimation, and then we can be more about it. So if I want to do that, then, well, I need to run this, all of the models that I have one by one, right? And once I have this run, then I pick the one which has the smallest, say, BIC. So let's do this. So let's say I have BIC to be a very big number, all right? So that's sort of the starting point. And then we say for P in, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. So that's all of the values. That's the range starting from 1 going to 9. And you have the arch model, so A model. So that's arch P, which is the arch model. So let's take this. Where P is equal to P, and then we do the estimation. Now we need the BIC, right? And I also need an if to see if I found the smaller indeed P. Here I would say if the arch P, arch at P, so let's use BIC, so dot BIC, so that will be the value of the Bayesian information criteria. If it is smaller than this big value, which I call big, right? If it is like so, then update big to arch P dot BIC, right? That's number 1. And then get me the P star. That's That's a very simple loop, right? You understand the logic. So, well, then we can print this. Let's do that. 9. So, which means that this is actually not enough. Right? So, probably when we hit the boundary, so probably we can make the BIC smaller if you are going more. But that's not interesting. Yeah, you remember that. So sort of you start with MA, and MA 10 is better than MA 1, MA 20 is better than MA 10. So you would like to have more and more lambs. Here is also the case. So we would like to have more and more lambs. Alright. But as I said, so that's sort of not interesting. And as such, in the MA models that we have the ARs, because they are parsimonious, they're capable of capturing the dynamics with less parameters. And then, so if we need it here, then we also have the Garch terms. So that's sort of when Garch comes in, the generalized autoregressive conditional heteroscedasticity model, simply because we need to be more parsimonious when it comes to modeling the dynamics, so capturing the dynamics that you have in this series. Right. So, let's keep this. Right. So then add one more, or some basic max. So let's say plus beta 1 sigma t minus 1 squared. Alright, so then this is indeed, so this was an arch 1. Right. But this is a Garch because we have the lags of the volatility also on the right hand side. Then it becomes a Garch 1, 2. So we have 1 lag of sigma and 2 lags of omega. Right? Well, now that I didn't want to wipe that off, right? I want to show you with this little stuff that we have here that let's say we have an arch, a Garch 1, 1, like so. Alright. And then alpha, there is no alpha 2, but then we need beta 1 to be positive. So we need alpha 1 to be positive, beta start with the Garch 1, 1. I want to know what happens. Alright? Just to see what is this generalization. What does it mean? What type of model is behind it? Right? So if I do this, then ut let it be. Sigma t has a recipe that I can plug in for. Ut squared minus alpha 1 ut minus 1 squared. Okay? And that is this, so minus beta 1 sigma t minus 1 squared. Right? So ut is looking like so. Right? Simply in this et, then I plug in whatever I have for sigma t. But now let's look at sigma t minus 1 squared. And then look at this. Right? If I look at that guy, then I know that sigma t squared, let's take this to this side and this to this side, is equal to ut squared minus e. Right? Okay. So, which means that sigma t minus 1 squared is ut minus 1 squared minus dt. Right, so that is what we know. So it means that I can write this as ut squared minus alpha 1 ut minus 1 squared minus beta 1 ut minus 1 squared minus ut minus 1 as this. Do you agree? So for sigma t minus 1, then I use this equation. Now let's rewrite a little bit. That is, so I'm simply doing that. So
We lost on zero. When we go.
thank you very much. What do you mean by V lost? You're so polite, you know, it's you lost. But we are all together. You're on the same boat. Alright, let's now rewrite. So we'll take ut, we'll say it as it is, and then the other terms I will take to the other side. So here then we have ut squared equals alpha 0. Oh, now look, here I have ut minus 1, and then here also ut minus 1. Right. They go to the other side, they become plus. So here I have plus alpha 1 plus beta 1 ut minus 1 squared. Right, so these two together. So it's a minus times a minus becomes a plus. What goes to the other side becomes a minus. And then there is a right? So that's the Garch 1. Does it tell you something? Or does it remind you of anything? This is short. This is an R model. So the Garch 1 becomes R model. So that's a generalized autoregression, which is in R. And so that's the AR coefficient, right? So if I want the stationarity, what do you need for an R model? For an AR1 model? You need this. Then we need alpha 1 minus and plus beta 1 to be smaller than. And this is positive, so the summation should be positive. So we need the summation of alpha 1 plus beta 1 to be indeed positive today.
curves, alpha 1 beta 1, and so on and so forth. That will be a big expression. It's a little bit larger. Which is possible. So we can find the factors. Well, and you will see that it's bigger than 3. Of course, that is the same. Like arch, there's a generalized one, so it will become a little bit larger. And then the role of this gauge effect, this beta 1, is that it makes us independent from including so many arch effects, so many lines of P. So let's right away do this. So model choice for the graph. So here then we have the whole scene. We can also still do the just 2 minutes. It will take a long time. So let's say this is P. We do a W for Q in say 0, 1, 2. Now we do this. Alright, so that's the model. Q is equal to Q. Then we also have the Q star. So just do the same, but the loop will be 2 dimensions, on 2 hands. Alright? And then let's see, what is P and what is Q? So there's one more. Right, so it's not, remember P was before 9. Right? And at the moment that we add 1 gauge, then 1 will be good. Right? Alright. So then, well, let's do a gauge 1, 1. Just wait till the time. So then I hear a lot of keystrokes, and it means that we're trying to catch up. So I haven't still told you anything about the estimated coefficients except the resistance.
estimate the model and look at the coefficients. So that's omega. So let's add these two, let's say 79 and 18 is 0.97. Yeah. Yeah, so that's these two, right? 0.97. That's actually a very persistent process. The volatility is very persistent. Which is not surprising, as I say, because what that's a index, a market index. I just say it over and over again, so you always remember that market indices have volatilities which are very persistent. So they sort of remember the past for quite some time. I mean, this was also evident for the autocorrelation function. It was going down, but it was taking some time till it goes down. So which is indicative of certain class of models which are not for now. But let's actually look at the autocorrelation. Sort of, I mean, this model is supposed to tell us something about the volatility. Right? So the volatilities could be inferred or estimated because it estimates the volatility. Sigma t is a function of the class. And let's see them at least. Right? Not only look at alpha and beta and say, the summation is 0.98 and we are happy with it, but we can look at the estimated volatilities of the series. Right? What is it that we have here? So what we can do is we can say, let's do a plot. PLT dot plot of what is it? The data is called y. Right, so that's y. The index on the y-axis, and then let's look at the volatility of branch 1,1. So here, then we say conditional volatility. Then we have say the volatility. So that sort of is same variable we get. So that is branch 1. Alright. But let's also maybe look at the others, because we estimated an arch 1. I just want to compare them. And then we also had an arch, what was it, 5? Yes. So we also had an arch 5. This is how you get the volatility. So dot conditional volatility, then we simply calculate essentially all of the path of the estimated volatilities, and then we can look at it. And let's compare it. That would be very hard to see the work. Well, then let's do it side by side. Alright, let's compare just 1,1 with 5, because 5 is less interesting, and 1 is less interesting. Let's do that. That's behind it. Right? So they're almost the same. Right? That's good. So the arch 5 and gauge 1,1 are almost the same. Right? Almost. Like falling on each other, pretty much. Right? Which is not surprising. If you remember the volatility that we had with arch 5, I added the numbers, it came to 0.97. No, 4. And this is 0.97. Right? So the persistence that the orange gets, which is our arch 5, is more or less the same as arch 1,1. But arch 5 has more parameters. Correct? But indeed, Garch 1,1 is a good model, essentially. because AIC, so the information criteria chose it for us, that's number one. And then in practice, sort of for a long period of time, the people will understood that seems that Garch 1.1 is a very good model for a wide range of asymmetry terms. Not 1, 2, but rather 4. It looks like to be one fits all, more or less, in capturing the volatilities. Maybe, so these are the volatilities. What we could maybe do is, let's calculate YABS, so which is absolute value of Y minus NP mean over. Right, so not taking the power of 2, but really looking at how far the data are from their mean. Right? And here I will add the absolute value. Just want to know how does it really look like. So I have an absolute, oh, this is y abs. Abs. Alright, so you see, you don't really see, but here maybe we can compare. Let's remove this. Yeah, let's compare the orange and the volatilities in these absolute deviations. And whenever we have very big absolute deviation, then we also high. Whenever we have big absolute deviation, so we are a lot far away from the mean, right? Then the volatility is high too. Alright, so whether negative or positive, alright, so when we are negative or positive, then we have large deviations for a long period of time from the mean, then the volatility is high. So whenever here we have the peak, then there we also have the peak, which makes sense. Right? So the results of this large estimation are pretty nice because they are capable of capturing the strong deviation or the clusters that we have here. Right? So when this is big, then we have a cluster somehow or some time period in the data. All right. These are classical Garch model with their imprint or the results that we have. So they are capable of capturing all this. But then there are some variations. When I started with Arch, so it was easy to understand. And then we needed parsimony, then we add the Garch effect. Right? So then we have a different generalization. Right? So this functional form for the variables. Right? So we can actually go on and change this functional form for our own needs. And because that's flexible, there is no theory. I think this is the question you had in the very beginning. Sorry, I forgot your name. Lynn, with an H. So, Lynn, I mean, you asked me, so can we actually do a Baron model? Right? Why do we have this location and this state? I don't have the answer to you. Right? So why do we have location and escape? But the escape function is what we play with. Arch 1, Arch 1, Garch 1, 1. And that doesn't stop here. You can make up your own function. And then say, oh, I like this and I want to use it. Alright? And as such, there is no end to this function. Now that we are sitting here and breathing, there is somebody making a new one. Alright? So it just goes on and on. There is no stop. But some of these models are more used, widely used, somehow they're more meaningful, and then people seem to use them, and then they exist also in different, basically, softwares. Right? They are implemented over there. But if they are not, then you know ML. If you have a functional form, then you bring it in, pass it to an optimizer, and then you have your sort of estimate. So that's not a big deal. Right? So if you want to stay with this class of models. So as such then, Let's maybe continue a little bit with the slide. So there was the arch, and then we basically have the gauge. So with some estimations, one can show that the gauge is an infinite arch. That's sort of, that you say an AR1 model is an infinite MA. That's what we know. So here is also the same. That an arch model is an infinite sort of arch model. Right? So that is what we have. Arch 1, 1, arch 2, more parsimony as I just said. We will come back to this. This alpha 1 plus beta, we saw that it must be smaller than 1. I will do this variance for you. Estimation will be an extension. So, right? So this is what I want. Right? So Garch essentially has problems. Right? One of the problems is that you require these parameters to be positive. Right? So these are called non-negativity constraints. And you know when you have optimization where you have constraints, then what do? You write a Lagrangian. And when you write a Lagrangian, then the sort of the search space expands by 1 unit, becomes harder. On the other hand, in sort of optimization methods, when you come close to the boundaries of the constraints, don't perform good. You go there, the derivative doesn't exist, and the method doesn't know where to go. There's no numerics. So they are problematic. These non-negativity constraints are problematic. And then some people basically say, okay, let's just use some model which still captures the volatility but doesn't have the non-negativity problems. Do you know them? Uwe has just told you arch and gauge, right?
Yeah.
So now I say a bit more. So one of these models is something which is called E-gauge or exponential gauge. Okay. And there is the GJR and then gauge. Let's basically talk about E-gauge, just so that you see what it is. So E-gauge came by Nelson, that's 91, and then said, okay, instead of modeling the volatility level, all right, look at and so logarithm. A logarithm can be negative, right? So you remember the logarithm function? It looks like, so this is 1, it looks like so. Right? If the argument is 1, then you have 0. If the argument is smaller than 1, then you have negative value. Right? So it means that, well, here the left-hand side must be positive, but if I have an ln of it, then I don't care. It could be negative or positive. It doesn't matter. Right? So that became the Nelson model. So here we have an E-gauge 1, and then there is the utility. The U is not utility, but that's unobserved component. Sorry. So then we have the U, which we have here, the shock, right? And actually also enters in this specification. But we don't need U to go to the power of 2, all right? There we need it. So this one, we needed to have a positive value. And then the non-negativity constraints. But here in E-gauge, let's say the model that he suggested doesn't even take care of the U to the power of 2. U can just enter because we don't have any problem with the positivity. All right? But then there are also some other terms here. All right? Which I want you to understand. Let me go there. So you are cluster. That's a big illustration. Here, you don't want to come to this side. You're happy. So let's say we have x to be normally distributed between 0 and go back, so let's say I'm just opening a parenthesis. What is the expected value of x? And the second one? And what about this? Can you calculate it? Well, that's after the positive number. Can be zero. Right? Zero. Can be zero, no zero. Because this is the average expected value, mathematical expectation of a positive number, or the behavior is like that. Then you can just say, all right, so this is integration, the minus infinity to infinity, absolute value of x, absolute value, e to the power of minus x squared divided by 2, 1 over square root 2 pi dx. So we can take the integral. Well, that's that's positive, is positive. So the negatives are the same as the positives. So we can just count the positives, multiply them. Right? You agree?
Yeah.
So we can write this like twice integration from 0 to infinity of x e to the power of minus x squared divided by 2, 1 over square root 2 pi dx. Please do. Please cancel the exponential.
now you see this. This is what he derived. So look, I mean, this is the error term in absolute value. We normalize with the variance, square root of the variance. So this is mean normal with mean zero variance one. And now, when this guy has this mean, the expected value of this is that. Such that the expected value of this is how much? 0. This is 2 over pi square root minus the square root 2 over pi. So this is on average 0. And this is also on average 0. U is also 0. Okay? So it means that, so if I want the expected value of, I mean, like we had there, right? So here, so if I have sigma squared, right? So then if I take an expected value, then this will remain and this will remain and no other term, correct? Well, here it is in such a way that the expected value of this, on average, expected value of ln will be omega plus expected value of ln of sigma t minus 1 squared. And those are off. Alright? So they will not actually contribute to the average of the variance, ln of variance, which is a nice feature. There's also something more to this absolute value coming in here. That becomes a bit finite. So now we start a little bit to talk about finance. After such a long time. We are together. All right. Well, here we have an absolute value. So u t minus 1 in absolute value is equal to u t minus 1 if u t minus 1 is positive and u minus u t minus 1 if u t minus 1 is negative. Right? But if this is positive, then the absolute value simply goes in that limit. If it is negative, then we have to multiply by minus, so that we get a positive. Right. Okay. Now let's see what happens to that equation, this one, the whole thing, when u is negative or positive. So when ut is positive or negative. Right? So I'll just write this order equation. So here we have gamma ut minus 1 divided by square root of, I can simply write sigma squared. T minus 1. Plus alpha absolute value of ut minus 1 divided by sigma t minus 1 minus some constant. Square root of 2 pi. So I don't care for that. I mean, that was important so that we have a center element. Right? So this is what we actually did for us. Now let's see. If ut is positive, then this will be the same as that. Then I can write it like gamma plus alpha. And ut minus 1 divided by sigma t minus alpha square root 2 pi. So this is when ut minus 1 is positive. And then let's say it's negative. ut minus 1 is negative. Then we have gamma minus alpha. ut minus 1 divided by sigma t minus 1 minus alpha square root of 2 pi. So this is when ut is negative. ut minus 1 is negative. Alright. So when will these two be the same? When will the two that I have here will be the same stuff? How? Under what condition? When what I have here and there alpha is 0, then the two will be the same. If it is not 0, the two will be different. So I just wanted to highlight that this alpha makes negative and positive shocks have different effects on the volatility. Right? So if alpha is 0, then positive and negative shocks will have the same effect on the volatility. If alpha is different from 0, then positive and negative effects will have different effects on the volatility. Now let's see, what are these shocks? Right. Let's pay attention to the nature of the shocks. We're looking at the model. So this is the model. Right? When the shocks are negative, alright, this is negative. Then are the returns above the mean or below the mean? Below the mean. So when this is negative, then I have a mean, it's here, and then the returns are below. Then the return will be negative. So it means when the shocks are negative, then the returns are below the mean. So we expect them probably to go up because they're below the mean. It doesn't work with this, so below the mean. Otherwise the mean will not be the mean. So we need them to go up. So if the shocks are negative, what will you do? Will you buy the assets or sell them? Yes, you buy it. Yeah, so that's sort of, not that it's cheap, because you expect that the returns will go up. It's not about the price.
Yeah.
Yeah, the price, well, I mean, that's about return. Right? So that's sort of,
Yeah.
so if it is positive, then you buy. If it is negative, sorry, what did I say? If it is negative, then you are below the mean, then you buy. So because you expect that to. And if it is above, yeah, so then you may take different strategies. I'm not saying that you may do that. You don't actually make a decision based on one observation, right? So you don't look at it and then do something because that would be very costly. But every day you buy, sell, so not too much. But that's sort of the. I just want that you remember the sort of think of this logic. Right. So if the returns are negative, all right, then we are here. All right. The returns are today negative. Everybody buys. Because you expect the return to go up. Then what happens? Do you expect the volatility to go high or come down? Yes. So I start with her. She said that when alpha is not 0, then these functions, well, if they are 0, they will be the same. And I looked at the other half. I said, okay, when alpha is different from 0, then these two will be different. And now we go back. If U is negative, then the returns are 0. People will start buying. They won't. So you need to buy up. Right. So that will happen to affect, because everybody wants to have it. Right. So that will happen to affect the volatility. Right. So returns go up. All right. And then what is the relationship between the return and the volatility? And volatility. So when you buy, let's say we go buy something off the market, something risky, something that comes with a risk. Why do we do this? Why do we buy? Because we can earn money.
Yeah, high return.
Exactly. So we actually get a premium because, so this is something that market gives us, awards us, says thank you very much for taking the risk off me, pay you a premium. Right? So because I'm buying the risk, I get a premium. Right? So it looks like that the return and the volatility sort of they should have some relationship. Right? And the relationship is different compared to selling something or buying, because here I'm not talking about the volatility, I'm saying that the
have a negative or a positive return. So below the average or above the average. And then the investors actually have different behaviors, basically, in this situation. So they may sell bulk, alright? And then because there's different behavior, then the market will actually be sort of affected by these different. But so to speak, depending on alpha being 0 or not, then you may actually observe different behaviors in the market with respect to negative or positive returns, short long, or not. Right? So if alpha is 0, then there are people who don't care. Right? So is the return bit small or large, you just don't do anything. Right? But if you actually do, then this alpha will be some number. Right? So it will be some number different from 0. Which is indeed something which we call it the leverage effect. So you are leveraging some information to sort of start affecting the volatility structure. So which is indeed capable of, well, as I said, so leverage. That's called the leverage effect. So this alpha is capable of capturing the leverage effect. So the sort of the different behaviors that one may have in terms of negative or positive. Should we estimate this? Yes.
I was just wondering, like, so we haven't made any, assumptions about the sign of those kind of effects, right?
Sure.
Those are positive or negative. And, the one below that would be lower than the.
Well, this is a constant, so that doesn't matter.
Yeah. So,
So this is a smaller. If gamma is positive, well, let's say gamma is positive, then not. Right? Well, it doesn't matter if it is gamma negative or positive.
it doesn't matter.
Let's say alpha is negative.
Alpha is negative.
Say alpha is negative. If
Uh-huh.
alpha is negative, then the effect of past shock will become smaller on the volatility tomorrow. Right? If alpha is positive, then the effect of a past shock will be bigger on tomorrow. Right? On tomorrow's volatility. Right? So regardless of whether you are negative, whether you are here or there. Right? So if alpha,
I mean, like, so in this thing, I can say that I can conclude that the contributions of the return have like asymmetric contributions to the
That's
volatility.
sure, that's true.
Uh,
Right, so that's sort of, so here becomes bigger, here becomes smaller. Now let's say gamma is 0.1 and alpha is 0.2. Right? So it means that 0.1, 0.2. When you are above the mean, right, then the volatility will have, will basically increase with more return. So if return is high, and the volatility will be higher. So if the volatility, if alpha is positive and you are below the mean, the volatility will drop if alpha is positive, right? Which doesn't make sense. So alpha should be negative. Alright? I mean, in line with the usual understandings that we have for the relationship between the returns going up and down and the volatility. We can estimate it. But maybe before actually I continue with the estimation, we have time still. So let me tell you a similar model, which is capable of capturing the leverage effect, which is called the GJR effect, sort of model. Well, it's still in the framework of Garch, alright? But what these three guys actually did, the model is called GJR for the names. Then you have the Garch plus a little bit, which is depending on whether U is negative or positive. So if the shock is negative, then this indicator function turns off, this goes off. Alright. If the shock is positive,
negative, then it remains, then will be part of it, so the coefficient of u will be alpha 1 plus gamma. And if the shock is positive, then this goes off. Alright. So, then, well, I mean, the leverage effect here will exist whenever this is positive. So it means that you have a big negative shock, all right? So you are below, you want to buy, and the volatility will increase. Everybody, business clock runs, everybody calls buy back, all right? So things go up, all right? So volatility will increase if gamma is positive. But I mean, one should see the same in the direction of coefficients like this and that. I don't remember. I think Python actually defines this other way around. That this is 0 and 1. We have to check. In the GJR model. But that's another model which is capturing the asymmetric effect that you have for negative or positive shocks on the volatility. Right? So that's another one. But I mean, leverage effect existed for many years in the financial markets, but recently has been done. Right? So things have become a little bit more asymmetric because there are so many market players and then it's somehow so easy to trade. Like the negative, in the negative side or the positive side, there are so many people who do invest in different directions that the asymmetry has been very weak recently. Previously existed, but now not much. Right? So that was the GJR model. And maybe before I go to Garchini, we do estimate those guys. Alright? So, well, I mean, the nice thing about these models is that, well, first you can understand the volatility estimating. Right? So that's sort of volatility you can understand and estimate. The second nice thing about those is that this is volatility today as a function of tomorrow. So it's dynamic. So which means that we can use it to forecast volatility. So that's another nice thing about them. And then the other basic interesting stuff about these volatility models is that one can embed certain features of the market in them. So say movements of the shocks or sort of the returns in here in terms of the leverage. One can also do a little further. Right? For example, you want to know actually I had a master's student doing this for a thesis. So the market that he focused on was on semiconductors, so Taiwan and so on and so forth. So sort of some of the African countries that do this. And then the question was, I mean, there are also indices for this type of markets. And then the question was that, what are the exogenous variables that happen to affect the volatility, except the past information? All right? And then there were interesting results. So sort of my idea, or that I sort of gave to do that, was to include political cycles. So movements, you could say, the political cycles that one has. So in Southeast Asia, here, not here. And then they seem to have a very strong effect on the volatility of returns in semiconductor, sort of the markets that we have here. Or say the elements that you need for this industry. Right? So sort of the chemical elements that you require, so you have to buy them so that you can produce the chip. So that is interesting. So one can actually do a lot of stuff just to see what is it that moves the volatility up and down. Well, this is very simple. It looks at the shocks being negative or not. But one can do more. One can bring more conditioning variables. And then do further stuff. All right. So let's see. Extensions.
let's say model 1 is equal to arch model of y. But let's just start with maybe a GJR. Alright? This model. Oh no, it's not here. This. I want to estimate this model. Alright? So one arch effect, one gauge effect, and one asymmetry. So here then we have GJR 1, 1, 1. Alright? So one arch effect, one gauge effect, one asymmetry. Alright? So here that's actually very simple to do. You say P is equal to 1, Q is equal to 1. And if you remember there was an O, which I told you later I will tell you. It is here, this O term. That is the number of asymmetric. Right. Here we have just one asymmetry system. I'm going to have ut minus 2 times it minus 2 times gamma 2. That's 2. Here we have just one, so O becomes 1 in this basic set. So that is what we have. And then let's say we have the volatility to be gauge, essentially. So 1 is equal to gauge. And then here we say print GJR1 dot sum. Alright, so here then we have alpha 1, beta 1, and that is gamma. And gamma, well, that's actually very big, right? And gamma is positive, so that's sort of, well, and then we have leverage. Essentially, that's sort of, maybe I've forgotten, but I somehow had in mind that this value should be much smaller. Anyway, so here we see that there is leverage. The negative or positive shocks have different effects on the volatility. So of course we can get the volatilities for the for this. Alright. So that's AIC, PIC. When we choose models, then we can write 3 loops, one on P, one on Q, one on O. Right, so there will be 3 dimensions, and pick the one that is the smallest. That's not a big deal. So here we have leverage effect. Gamma is positive. So when the shocks are negative, then people buy. And the volatility goes up. So the business flow runs fast. So I will estimate also an E-gauge model, and then we'll do multivariate.